So this is the control room for Alice and Emma, and they are particle accelerators at Daresbury Laboratory. So usually we're not allowed to enter the accelerator area because of the radiation, but once a day we ramp down and switch off, and we're going to do that in a minute. And everybody who goes in takes one of these keys and puts them in the back pocket, and the power can't be turned back on, and we can't ramp up the high voltage unless all of those keys are back in. So it's just to double check and ensure that there's absolutely nobody in there before we turn on the high voltage. So in between the control room and the accelerator areas, we have a labyrinth of concrete blocks. They are here to stop the radiation when the machine is running. Okay, so what we're looking at is, here we have part of Alice, and over there we have Emma. Here we let everything hang out. We have all of our accelerator components exposed in a large access area. And the reason for that is so that we can change the configurations of the machine and find out what works and what doesn't work. Most particle accelerators are dedicated user facilities, so they are there to be very reliable and to work all the time and have exactly specified operating modes. Whereas here we're developing the particle accelerator technology itself. The electrons in a beam travel through this pipe here, and this pipe is kept at ultra-high vacuum. So the vacuum inside this pipe is stronger than that on the moon, for instance. And we need to do that because if the electrons see any air particles, they'll scatter off them and spoil our beam. So the point of the magnets is to focus the beam, in the case of these, because these are quadrupole magnets. So they're kind of analogous to a lens, like this one here, but for charged particles. There's nowhere else in the world that has one of these machines. So we're working with a world first. The ring is Emma, and Emma stands for Electron Machine of Many Applications. And we have the extraction line, where we diagnose the beam as it comes out of Emma, and we have the injection line, where we put the beam into Emma. And the beam comes out of Alice. So it's the world's first type of particle accelerator called a non-scaling fixed field alternating gradient machine, which is a very fancy term, but what it really means is that we're trying to make an accelerator that can accelerate beams like the Large Hadron Collider or Diamond Light Source, but be much cheaper. Because if we want to use particle accelerators for other sorts of applications, so in hospital treatments or even in power generation, we need to be able to build particle accelerators cheaper. So we've talked a bit about Emma, and now when we go through the wall, I'll talk a bit more about Alice. So this is our DC photo injector. So what this is a 500,000 volt power supply, and this is the electron gun. It produces electrons. They are accelerated in that direction towards the rest of the machine. So the electrons, when they come out the gun, they've seen a voltage of 350,000 volts. But we want to accelerate them up to truly relativistic speeds. We want to get up to 35 million electron volts. And the way we do that is in our superconducting niobium cavities. They are made of this rather rare metal called niobium. Niobium has a very special property, that when you cool it down to 2 degrees above absolute zero, it becomes superconducting, so it loses all electrical resistance. Now, we need that because if we were to put the amount of power that we do in our beam into accelerating structures that are lossy, have electrical resistance, then they would heat up and pretty much melt. So we've accelerated our beam up to 35 million volts, and this is where the business happens. This is the business end of the machine. And what we do is we do some gymnastics with our electron bunches. We make it such that they get shorter in this thing. In effect, the back of the electron bunch catches up with the front of the electron bunch, and in that way we make it short. Now how short? We make it about 1 picosecond long. So that's 10 to the minus 12 seconds it takes to pass any point. And we're packing enough photons in there to be the same amount as all the photons emitted by the City of London. The difference between ALICE and machines such as the diamond light source is that ALICE is able to produce very short pulses of light. And you can think of that as being like a video camera. So you shine very short pulses of light lots of times at some sample. And in doing that, you make not just, you get information not just about the structure of that, but also the time information. So you can in effect watch chemical bonds breaking and watch chemical reactions occurring. Particle accelerators are a tool. What we're doing here is we're advancing the science of the tools itself. So we are making new forms of particle accelerators that will be the better tools for the science of the future.